you don't see it all at once. But sine and cosine. If I'm talking about the sine and cosine in terms of thinking about graphing and domain and range, you have to kind of separate that from the unit circle. So let's say I said, we'll just use sine. The sine of t equals something. I'm just going to say that equals f of t. Kind of trying to get away from x's and y's a minute just because we get that confused a little bit. After we take our test, we're going to graph sine and cosine, like on an xy plane, and we're going to learn how cool they are. We're going to graph all of them, actually. And we'll talk about this a whole lot more. But I want you to see at least the idea about the domain and range of this. Sine of t, the domain would be like the t values. Could I plug anything I want in for t? Could I plug in the sine of 762,000? I could plug in the sine of negative 2.6. Like, I could plug in anything. We like to plug in nice, like, pi 6 and pi thirds because we get cool answers out of it. But you can really take the sine of anything you want and the cosine of anything you want, which is why the domain of sine and cosine is all real numbers. So we're going to say negative infinity to infinity because you can take the sine and cosine of whatever you want. But the range of sine and cosine is definitely not negative infinity to infinity. And you can use your unit circle to think about the range. The range is the output that we get. When we take the sine of something, what do we get? Take the cosine of something, what do we get? And if you think about this, on my unit circle, this is the point 1, 0. This is the point 0, 1. This is the point negative 1, 0, and 0, negative 1. For my x values, which are cosine, what is the biggest x value that I ever get going around that circle? 1, right? Because think about if we connected this, this is not going to be a very nice looking circle with my picture here. Oh my gosh. Oh. Theoretically speaking, if that was a nice circle, do you agree that the points in between here are not bigger than 1 and negative 1? Yes? Like when we do our special numbers in here, like this is square root of 3 over 2, 1/2. If square root of 3 over 2, that's smaller than 1. Yes? Square root of 2 over 2 is smaller than 1. Like all of those are smaller than 1 in between there. And the same thing over here. They actually just keep getting negative and negative until we get to negative 1. And all of our cosine values are stuck between negative 1 and 1. No matter what angle you could think of. The biggest angle you could think of, guess what? Its cosine is going to be somewhere between negative 1 and 1, because that's the only value that you can get. And the same thing is true for sine. Sine is the y-coordinate, and the biggest y-coordinate you ever get is 1, and the smallest y-coordinate you ever get is negative 1. And every angle that you could ever think of is stuck in between there. So the range of sine and cosine is between negative 1 and 1. And we graph that, that'll seem a lot easier. But what's really cool about that is no matter what angle you get, it's going to be stuck somewhere in between these values. And so I kind of try to show you the relationship between the y-coordinate is the sine, the x-coordinate is the cosine, so that's what you can say on the unit circle. But here's kind of the big thing. We call these functions periodic functions, and that word periodic means that they repeat themselves. Sometimes they say they're wrapping functions, but not like wrapping like, ooh, wrapping, I'm cool. Like wrapping like W wrapping, right? With the W there. I mean, like it wraps around over and over and over. And we've talked about this in terms of coterminal angles. Coterminal angles, you can take any angle and you can add 2 pi or you can subtract 2 pi and you're in the same spot. But the value of sine and cosine will be the same. And that's what's kind of cool and maybe kind of confusing about these functions, is that you could add any multiple of 2 pi to an angle that you already know, and it would be the same. So I think there's one on your homework that says, like, I'm going to make up my own here. But the sine of pi force plus 10,000 pi. It says, hey, what does that equal? And the idea is, if you add some multiple of pi, they don't really expect that you draw that circle and you're like, okay, pi force. I'm going to go around 2 4 pi, 6 pi, 8 pi. They don't expect that you just keep doing that till you get to 10,000 pi, right? The idea is if I go around an even number of pi, will I end up right back there at pi fourths? So I don't have to draw a picture. I can just say, hey, I know that's the sine of pi fourths. And what is the sine of pi fourths? The y coordinate at pi fourths is the middle one. So it's supposed to make finding sine and cosine values easier if you just add or subtract 2 pi. That's why on the ones that are like 29 and 31 and those ones that said like use a reference triangle or use a unit circle, when they give you an angle bigger than 2 pi, just subtract 2 pi to get back in the circle. If they give you a negative angle, just add 2 pi because we're allowed to do that because we know it's going to be the exact same. Okay? Periodic functions. And so this kind of just defines what a periodic function is. The periodic function, if there exists some value that when you add it to an angle, you get back the exact same thing. We already know what that is. And we call that, kind of a weird thing here, we call that the period of sine and cosine. So how long does it take for me to start at an angle and get back to exactly where I started? Is 2 pi, right? So the period of sine of t and the period of cosine of t, we know, is 2 pi. That's how long it takes us to get back. So that's why we can add and subtract 2 pi so easily to get back where we are. And so that means I wrote at the bottom here that all of these have the same value. And so sometimes people think that they're wrong because they just keep getting the same answer over and over again. But if I gave you those 4 problems, it's the exact same answer because if I'm over here at pi and I add 2 pi, I'm now at 3 pi. And if I add 2 pi again, I'm at 5 pi. And if I add 2 pi again, I'm at 7 pi, which means all of those have the exact same value, which would be, what is the ordered pair over here at pi? And sine is which one? All of those have a sine of 0. So when we start graphing these, we're going to talk about when we do, remember all those translations and stretches and shrinks and all this fun stuff that we do with graphs? We can do that with sine and cosine too, which means the period can change. So a little funny story. Did you guys have Mr. Mullis, or at least know of Mr. Mullis? You're too young. He said that when he was student teaching, like his professor, like when you're student teaching, your college professor comes in to grade you, and he was teaching trig when his college professor came in, and they were talking about the period of sine and cosine. He put this problem on the board. He's like, okay, so what's the period of this? And they all just stare blankly at him like you guys tend to do to me on a daily basis. And he's like, come on, guys, we know how to do this. What's the period of this function? And they just stare at him. And so he got really flustered because his teacher was there. And then finally he's like, guys, how long is my period? And then all the kids started laughing because he said, how long is my period? And he was really embarrassed. Every time I teach this, I always think about how long is Mr. Mullis' period. So just a little laugh on the inside for me. One day at lunch, we had a big talk about our most embarrassing teacher stories, and that was his that I tend to share with you every year. So it's not going there. It's too embarrassing. I'm not going to say it. But. Maybe someday. Someday I'll tell you. There's lots of embarrassing moments, but one that I'll tell you, that's probably not my most embarrassing, that wouldn't embarrass me to tell you, is one time when I was teaching like infinitely many solutions, no solution, or all real solutions, right? Like no infinitely many, no solution, I don't know, like when you do like intersecting lines, and so I'd be like, you can just write no SOL, or you can write infinitely many SOL, and all day long, my Algebra 1 kids kept laughing, like, SOL, and they would laugh, and I'm like, what does that mean? Like, am I missing some texting lingo? Like, I don't even know. And in the very last period of the day, I was like, SOL. Oh my gosh. And so then I was embarrassed that I've been saying SOL all day. And it's an old saying. I mean, if you don't know, you ask your friends, because I'm not telling you what it stands for. But it's like what grandmas say. But I was saying that all day, like just saying it to everyone, and then I thought it was some new texting lingo that I wasn't aware of. So now I don't say SOL. I just say SOL, or I just say solutions, as I like to say. Sometimes as teachers, you say things that you don't mean to come out in a way that they come out, and then high school students always take them in an inappropriate way. My most embarrassing is a student teaching moment also that I'm not going to say because it's really embarrassing. Even in odd functions, this is something that we're going to talk about even more when we're graphing. Not a big deal right now, but just be aware that even functions, we talked about last semester, right? X squared is an even function because when you plug in a negative number, you get the same thing as when you plug in a positive number. Yes? That's true with cosine and cosine's reciprocal. If you plug in a negative angle, guess what? You get the same thing as a positive angle. You don't have to know that because you can just find the angle, or you can just do the negative angle, or you could just add 2 pi. But if you wanted to, if they asked you to find the cosine of negative pi halves, that's the same as the cosine of pi halves because it's an even function. So if you know that and you see a negative angle, you can be like, oh, I can just do the positive angle. I don't feel like it's that necessary right now. When we graph it, we're going to see it's important because when you graph an even function, it's symmetric about the y-axis. And we're going to notice with cosine and secant, it's symmetric about the y-axis when we graph it. So I always remember this is the only even one and all the rest of them are odd. So I never like think about I need to memorize all this. I always just think cosine and secant are even. The rest of them are odd, which means if you plug in a negative angle, you're going to get a negative value. So to plug in a real number here, you could say the sine of pi 6, negative pi 6, is going to be the opposite of sine of pi 6. And we're going to see this again in the second half of this chapter. When we solve trig equations way down the road, this will come into play more. When we do some trig proofs, doesn't that sound exciting? We'll use this a little bit more, but right now, not that important. Trigonometric proofs, my favorite thing to do. It's good. So I think I have a couple examples here. I'm gonna do. Right? Are these on your paper? I don't think I've given you these yet. I think that's the big hunk of homework that's left from this section. Is they like to give you values here, and this is where I think you got to use the unit circle because if you're at 0 or pi halves or pi or 3 pi halves, using that ordered pair is so much easier. And remember, if they give you a big angle, that you can always just subtract 2 pi. So for me, when I see 7 pi halves, I automatically know that's not on my circle because do you agree that's bigger than 2 pi? So you have two options. One option is you can just think about where that is. That's 3.5 pi. You just think about 2 pi, 3.5 pi. Or I think the best option is when you see a number bigger than 2 pi, just subtract 2 pi from it until you get an angle that's in our circle. And if you subtract 2 pi from that, that would be 4 pi halves. 7 pi halves minus 4 pi halves is 3 pi halves. And you should be able to tell me where is 3 pi halves on the circle. And what is the ordered pair at 3 pi halves? And cosine is which one? X. So guess what? The cosine of 7 pi halves is the same as the cosine of 3 pi halves, which is the x coordinate, which is just 0. Again, definitely what would show up on a no calculator part of your test. A lot of the no calculator stuff, there's not a whole lot of work to go with it. It's just knowing the values. And if they give you a negative angle, by all means, you're welcome to go backwards and graph negative. That works. But I never do that. I always say, I don't like negative angles. I want to make it positive, so I'm going to add 2 pi. And that would be the same as saying the sine of pi halves. Pi halves is up here, and the ordered pair is 0, 1, and sine is which one? Y, and the y coordinate is 1. The answer is 1. That's the majority of your homework that's left. If you did the part last night that you're supposed to do, is doing stuff like this. And almost all of them are here, 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 here. So guess what? Your answers are 0, 1, or negative 1 every time. Because that's what all the x and y values are on the axes. I think that's 4-3. That's last new stuff that's on your test. So The green stuff is what is called day 4, which is not on your assignment sheet. But you got to do all of this at some point. If you haven't done it all, you're welcome to do it all on the same page. But 37 through 42, and then 49 and 50 are what you should have added on to your homework today. Again, if you feel like you have no clue what I'm talking about up here when I'm talking about the triangles or the unit circle, you really need to start studying. I can't express how important it is that by the time we have a test next week that you have some clue what I'm talking about. Hopefully a big clue of what I'm talking about for this stuff. So, we have a good amount of time left. So maybe, no embarrassing story, but let me give you this unit circle worksheet that's just a big unit circle for you to fill in, and we can watch the unit circle song while you fill it in, and then I'll be quiet and let you work on your homework. Okay? It's a good song.